Okay, so today we're looking at a specific type of series, and we're looking at what is called the geometric series. So specifically, it is one in which every term in the series is obtained by multiplying the previous term by a value r. So this is going to be our definition, and let's just take a look at an example. If I have a series where the first term, the value is 4, then I want to multiply this by a certain value called our common ratio to get the next term. So let's suppose that we're going to multiply it by 3 so that our next term is going to be 12. Now we do that again, we multiply 12 by 3 and the next term that we put in our series would be 36. We can keep doing this, repeating this pattern. The very next term that we add up, it's going to be plus 108, and we can keep doing this forever. And what you end up getting here is called a geometric series. Okay, we're going to have our counter starting off at 1, and we want to see what are the terms that we're adding up. So the notation that we're going to use is going to look like this. So first off, we have 4. That's going to be the number here that we started with, and then 4 is going to be multiplied by 3 every time. And as our counter n increases, so is the exponent on 3 going to increase. And so this is very much what this series would look like. You'll notice if I look over here, when n is equal to 1, that means that this exponent of n minus 1, that's going to be 0, and the first term is just going to be 4. Then to get from 4 to 12, we're going to go here and we're going to multiply by 3. And now if n is equal to 2, we have that this is going to be 3 to the power of 1, which is 3, multiplied by 4, and that gives us our second value in the series, which would be 12. Okay, and then this series keeps on behaving in the same way. Every time that I increase the value of n by 1, I'm going to be multiplying again by 3, and that's going to go from 12 to 36, and then from 36 to 108, and so on. We want to know what happens with this geometric series as n increases without bound. If I add up all of these terms, is this series going to be convergent, or is this series going to be divergent? Now, we're going to be answering that question in a moment, but let's also introduce a little bit of notation at the same time. So first off, the value that we start with here at the beginning, that's going to be a, and we're going to add in the restriction that a cannot be 0. So if I start off at a, and that's my first term, then the second term will be a multiplied by r. Okay, again, we're going to be multiplying each term by r, and r is our common ratio. So then we're going to multiply again by r. We have a times r squared, we have a times r to the power of 3, and we're going to keep doing this forever. Our counter is going to start at 1, it's going to go to infinity. We're starting off, the first term is a, and we're multiplying every time by the common ratio, and as n increases, we're going to be increasing the exponent on that value of r. So here, let's just sort of make that note. R is called the common ratio. And now that we've seen sort of how to picture a geometric series, okay, again, a geometric series is just one where to get from every one term to the next term, you're going to be multiplying by a common ratio. Let's take a look at how we can tell when a geometric series is convergent and when a geometric series is divergent. Okay, so here we're going to look at a geometric series, and we want to know when does this series converge, and at the same time we'll figure out when this series diverges. So what we're going to have to do is look at quite a few different cases, okay, and we have to remember that if we want to look at a series, then we can tell our series is going to be the same as doing the limit as n goes to infinity of our partial sums. Okay, so we want to take a little bit of a closer look at our partial sums here. And first case, let's break this down into the first case where we're going to say that r is equal to positive 1. Okay, so our common ratio here is positive 1, and in that case, what happens with our geometric series? Well, it doesn't matter what a is here. Remember that we have made the restriction already that a cannot be 0. So we're adding up, starting at 1 and going to infinity, a multiplied by the common ratio, which for us is going to be 1 in this case, to the power of n minus 1. And really, what this means is that the first term is going to be a multiplied by 1 to the 0, so it's just going to be a. And then it'll be a multiplied by 1, and a multiplied by 1 squared, a multiplied by 1 to the 3, and so on. Really, what we have is a plus a plus a, and so on. What we want to know is, does this converge or does this diverge? Well, it might be clear right away that it's going to be divergent, but we can do that using our partial sums by saying that here the nth partial sum is just going to be a plus a plus a. All the way, how many times? Well, it's going to be a added up n times. So our partial sum is going to be n multiplied by a. And therefore, if I'm going to do the limit as the number of terms in our partial sum goes to infinity, that's going to be the limit as n goes to infinity of na, which is quite clearly going to be infinite. It doesn't exist, and therefore we have divergence. Okay, so that's the first case. If the common ratio is 1, we end up with divergent. So let's take a look at the second case. What happens, for example, if r is equal to negative 1? So if r is equal to negative 1, then our series is a multiplied by minus 1 to the n minus 1. And now if n is equal to 1, we have minus 1 to the power of 0, which would be positive 1. So the first term is going to be positive a. However, if n is 2, we have minus 1 to the power of 1. Okay, and minus 1 to the power of 1 is just going to be negative 1 multiplied by a. That's going to give us just negative a. That's the second term. And every time this value of n increases by 1, all that's going to happen in our series is that the sign of this is going to go from positive to negative, back to positive, and so on. So the pattern is very much going to look like this. Okay, we have a minus a plus a minus a, and so on. So we want to know, does this converge or does this diverge? Again, we can do that by looking at the partial sum. Okay, so the partial sums in this case, actually let's give ourselves a little bit more room. The partial sums are going to be a little bit odd. Okay, they're either going to be equal to a, or they're going to be equal to 0. So for example, if I look here at the first partial sum, that's going to be just the sum of the first value. It's going to be a. If I look at the sum of the first 3 terms, it's also going to be a, and the sum of the first 5 terms would be a, and so on. So s sub n is going to be equal to a if the number of terms being added up is odd. However, if the number of terms being added up is even, then that means you're perfectly going to have all of these terms canceling out with each other, and the sum would just be 0. So what does this mean? It means that if we now go and do the limit as the number of terms goes to infinity of s sub n, what happens with that limit? Well, it's going to keep bouncing around. It's going to keep bouncing around back and forth between 0 and a as n goes from being an even number to an odd number to an even number to an odd number. And so really, this limit is just going to be one that does not exist. Okay, it does not approach any one single number. It continues to bounce back and forth between the two values 0 and a. So that means also, again, that our series is going to be divergent. So we have our series, the geometric series diverges for r equal to 1. It diverges for r equal to minus 1. Now let's take a look at some other values of r. What if r is less than 1? What if it's larger than 1? And so on. So if r is not equal to 1 and it's not equal to minus 1, this is where things definitely start to get a little bit more interesting. So here, let's take a look at another case. What if r is not equal to 1? Well, again, we need to come up with some way of finding our partial sums. However, in this case, we could say that our partial sum is a plus ar squared, ar cubed, all the way down until we get to the very last term. Now, what is going to be the last term here? Well, we're adding up all of the terms until we get to capital N as our counter. So the last term will be a times r to the power of capital N minus 1. So that gives us s sub n, our partial sum. Now, here, let's do something a little bit weird. Let's take a look at r multiplied by s sub n. And if you multiply this partial sum by r, what do you end up with? You end up with the first term here being a times r, the second term will be a times r squared, then a times r to the 3, a times r to the 4, and so on, with the last term now being a times r to the power of capital N. Well, let's take a look at one of them, s sub n minus r times s sub n. Okay, and let's see what happens with this. So if I do the first one minus the second one, you'll notice almost all of these terms are going to cancel out. I could take this a times r with this a times r. They're going to cancel with each other. This ar squared, those are also going to cancel. Ar to the 3 is going to be gone. This term would cancel with the term that would be right here, so it is also gone. And this term right there would cancel with the term that would come right before a times r to the power of n. So it is also going to be gone. The only terms here that do not cancel, okay, the only terms that do not cancel are going to be this a at the start and this a times r to the power of n at the end. Okay, so this is a little bit reminiscent of a telescoping series. There's sort of that same cancellation effect, but here we're actually looking at the difference between two of these values, one the partial sum and one the partial sum multiplied by r. So this is just more of a trick than anything. If I do one minus the other, everything cancels out except I'm left with a minus ar to the power of n. Now, that's fine, but what do we actually want to do with this? Well, our goal was to find a nice formula for our partial sum, okay, for s sub n. So now I have s sub n 2 times on the left, but I can just treat it as any other unknown. I can factor it, so I have s sub n multiplied by 1 minus r. That's going to be equal to a minus a times r to the power of n. And then I can just divide through here by this 1 minus r to end up getting that our partial sum is going to be equal to a minus ar to the power of n divided by 1 minus r. And that's a nice enough formula. Okay, what do we want to do with it? Well, now we want to take a look and see what happens here as the number of terms in our partial sum goes to infinity. So let's take a look at that limit. Okay, we want to check what is the limit as the number of terms goes to infinity of s sub n. Does this limit exist? When will this limit exist? So here, at the same time, let's go to our numerator, a minus a r to the capital N, and let's actually just factor out a, so that leaves us with 1 minus r to the power of n, all divided by 1 minus r. Okay, so this is the limit that we want to do, and we've already broken it down into cases now where r is not equal to 1. Okay, so we don't need to consider anything about this denominator being 0. We've assumed r is not 1 and r is not equal to minus 1. So now let's take a look at what happens. So here we're going to add in 2 more cases. Okay, and in this case we're going to take a look at when the absolute value of r is going to be less than 1. Okay, what happens if the absolute value of r is less than 1? If we have a small value of r, what happens? So here, if I notice that I'm doing the limit as capital N goes to infinity, you will see that only this one term in the limit depends on the value of capital N. So all that we are interested in now is what happens to that one term as capital N goes to infinity. So here, as capital N goes to infinity, what happens to r to the power of n if the absolute value of r is less than 1? Well, think about these terms. If absolute value of r is less than 1, this limit is going to get smaller and smaller every time you multiply r by itself. If I have a value of r that's less than 1, something like 1/2, and I keep on multiplying it by itself, each time I do so, it just gets smaller and smaller and smaller. So here, this limit is going to be 0, and what that means is that the limit, as capital N goes to infinity, of a times 1 minus r to the n over 1 minus r, this term we know goes to 0, so the whole limit is going to exist. It's going to be equal to a divided by 1 minus r. And these values, we don't know what they are, but it exists. And so we would say that the series here is going to be convergent. Okay, and if it is convergent, it's actually going to be equal to that value. That's the limit as n goes to infinity. So here we can add that in, that our summation of our geometric series would actually be equal to a divided by 1 minus r. So that's the case where absolute value of r is less than 1. Let's take a look at one final case. What happens if absolute value of r is larger than 1? What if we're looking at large values of r? Well, then we can take the limit again as capital N goes to infinity of r to the power of n. And now every time I take my value of r, let's suppose r is larger than 1, and I multiply r by itself over and over and over again, that limit is just going to continue to increase. It's going to increase without bound, and so this limit is going to be divergent. It's going to go to positive infinity if r is positive, and if r is negative, it's just going to diverge. It's going to be increasing without bound, but it's going to be bouncing back and forth as a positive number and then as a negative number and so on. So here, what we'll do in general is that this limit just does not exist if r is going to be in absolute value larger than 1. And so what we would say is that our limit as capital N goes to infinity of a times 1 minus r to the n over 1 minus r, this limit itself is also not going to be existing, and that means that the entire series is going to be divergent when absolute value of r is larger than 1. So if we go back through our cases now, okay, we have looked at all of the different values of r. We have here divergence. We also have divergence when r was equal to minus 1 and when r was equal to positive 1. And actually the only time that we ended up getting convergence was when r was less than 1 in absolute value. So let's sort of summarize these results. And what we get is that the geometric series ar to the n minus 1 is going to be convergent if absolute value of r is small, if the absolute value of r is less than 1. And in that case, we end up getting that our series, not only is it convergent, but we will know exactly what it's going to be equal to. It's going to be equal to a divided by 1 minus r. So that's the first case here. That's when we have convergence, but for every other value of r, we have divergence. So that's if absolute value of r is larger than 1, or if absolute value of r is equal to 1 as well. And in that case, we're going to have divergence. So now that we have seen what happens with a geometric series, specifically, we know how to tell when it is going to be convergent and when it is going to be divergent. Okay, everything is based off of these values of r. Let's go and actually just take a look at a couple examples. and you'll see it's a very useful result. We can usually tell now almost just by looking at a geometric series if it's going to be convergent or if it's going to be divergent.